Okay, let's start this plastic gear calculation web demo. Hello everyone, welcome to the KISSsoft plastic gear calculation web demo. I'm Aljaž Pogachnik and I will be your presenter today. There are over 50 participants now, so I hope you all hear me well. If you have some questions with the sound, you can try to call in with your phone. Maybe it will work then. All the participants are currently muted, but nevertheless you can ask some questions via the questions or question window in this web tool. My colleague Ilya Tsikur will answer this writing in live, and if at the end there are some open questions left, we will answer them. Also, we have prepared some documents for you, which you can find in this GoToWebinar Handout tab. Okay, let's start with the agenda for today. First, we will talk about plastic material data in KISSsoft, what is needed, which materials are available in KISSsoft. Then we will run through the calculation methods for plastic gears, for cylindrical plastic gears, and also for cross-helical worms. We will do some example calculations for spur gears and also for cylindrical worm gears, and at the end, a short topic on plastics manager. What you see now is an overview of the plastic materials that we have in KISSsoft database. Currently, we have 56 materials available. 24 of these materials are, we call it open source. So when you install the software, you get the materials with the installation. These materials are usually from the standards or industrial measurements, or they are also provided to us by the material manufacturers like Courray or DuPont. We also have 32 specific materials which are on request. 22 from these are from Savic, then we have some from Alcom, DSM, Victrex. It means that when you install the software, you don't get these material files with the installation, but you have to ask for these text files and then we send it to you. This is basically the request from the manufacturers or from the providers of the material data, so that they a little bit gather the information who is using their materials. We have 36 materials where you can calculate root fatigue. Flank fatigue you can only calculate for 10 materials, and wear data is available for 44 materials. A short summary of what material properties are needed or what material properties are available to add into KISSsoft database. The basic material properties are yield and ultimate tensile strength as a function of temperature. We also need E modulus as a function of temperature and Poisson ratio, just as one value. Optionally, we can add wear factors for different material combinations, and if you want to calculate lifetime fatigue safety factors for the root and flank, we need the SN curves. Also as a function of temperature, and these SN curves are the most difficult to obtain. A few words about this will be also at the Plastics Manager. Let's see how this looks like in KISSsoft. I will open the KISSsoft database. And here you have if you want to add a material to use it in gears, you have to add it at two places. So material basic data and material of gear. First we check material basic data. And here I can search for POM material, for instance. If I double click, you get an overview of some basic material properties like Young's modulus, Poisson ratio, density, specific heat capacity and conductivity. These two values are just for information. Coefficient of thermal expansion. This is needed for the operating backlash calculation. Shearing modulus is also just as an information available. What you can also add is you can also add tensile strength and the diameter at which the tensile strength was measured. This is basic material data. If I close this one, then we go to material of gears, search for the same material. Here you can see the basic material, which was POM in our case, and here we also have to set it for the gear data. Then we have some comments here that we can add with some letters. This means this has specific meaning for plastic gears, and S stands for data is available for static calculation. It means that yield and or ultimate tensile strength is available. B stands for root fatigue data. F stands for flank fatigue data. W stands for wear. WD in this case means that wear factor for dry running is available. We also have then O for oil and G for grease. C stands for cross-helical gears. Basically, it means that the shear SN curve is available for cross-helical gears. The most important thing for plastic materials is that we can define here a text file for Velar line basically, but it also contains more information about the material itself. I can click here to see how the text file looks like. Basically, this is just a text table that can be modified by the users, and it contains the following information. We have the coefficient of friction for oil, grease, and dry running. We have E modulus versus temperature. We have ultimate tensile strength versus temperature and yield tensile strength versus temperature. And then we have SN curves basically. What you see here is we have temperatures here. In the first column it's number of cycles, and in between are the allowable flank stresses in this case. Such table is available in this case for oil, grease, dry running. So the highest allowable stresses are for oil lubrication, and then the smallest are for dry running. This is for flank, and then we have also the same structure for root fatigue data or root strength data for the root calculation. Here we have an example of several SN curves for plastic gears. The problem of plastic is that the material properties depend heavily on the temperature changes. It means that also the SN curve has to be a function of temperature. And because we have to measure it at different temperature, it means that we have several SN curves for one material. And in this case, if you take a look at the red lines, you see 5 different SN curves. Each one corresponds to different temperature. If you want to measure it, it means that the test durations or the time period in which the tests are run is much longer compared to measuring SN curve for steel gears. About this, we will maybe say a little bit at the end. If we go now just to the end of the text file, what we have at the end is wear factors. We can add them also as a function of temperature, and we can add separate wear factors for dry, grease, and oil lubrication. Now we can move to cylindrical gears in general. First, a small introduction on calculation methods. In 1981, the VDI 2545 was introduced, but it was retracted in 96, basically because it was never reviewed properly. So the basic calculation, this is guideline, not a standard, had some material properties for a few materials, and also had some SN curves available for a few materials like PA66 or POM. Between 96 and 2008, we didn't have any valid guideline calculation method, and we also didn't have any additional material SN curves available. In 2008, and from 2008 on until today, and also for the future, we are adding some material on a yearly basis to our KISSsoft database, and the SN curves are either measured by some industry measurements or by the manufacturers of the materials. Uh, Around the year of 2013, the new VDI 2736 was released, and this is now the only valid guideline that we have to calculate the strength of plastic gears. Let's go to the software to see how this looks like. I've opened an example from before. Let's first take a look at the temperatures, which are very important for plastic gears. If I am in the tab Basic Data, and here on the right side of the lubrication, I can press the plus button, and I get the Define Temperatures window. Here we can set manually the temperatures separately for the root and flank for each of the gears. Or we also have an option to calculate temperatures on the root and flank based on the calculation equations from the VDI guidelines. The problem is that if you use this option, calculate temperatures, it uses the equations in the VDIs, but the problem is that the equations are not really precise. So what we always advise to our customers is that they should enter the temperatures manually for the root and flank, either based on some experiences from before or based on estimation of temperatures. So in this case, I will set the temperature on all gears to 50. Maybe this option to calculate temperatures could be used when you are comparing two different designs, but I wouldn't count on giving us the absolute correct temperature during the meshing. So in our case, we will just set all the temperatures to 50. We have PA66 on the pinion and POM on the gear. Let's check the calculation methods. So for plastics, we have 3 calculation methods available in 2018 release. So we have the new VDI 2736, YF method C. YF method C means that the application point of the force on the tooth is at the tip diameter. And method B means that the application of the force is at the point of single tooth contact. I will show you then the comparison between the two calculation methods. So we have the new VDI and we have 2 options for the old VDI, YF method B, YF method C. For plastics, we also have the static calculation. And in some cases, we can use also the ISO 6336. I will also show you later. Let's do a calculation with VDI YF method B. If I calculate, in the results window, what you see is you have a root safety and a flank safety factors available for both materials, for both gears. For instance, if the flank SN curve is not available in the text files, the safety factor here will be just 0. And you will get a warning message that the fatigue data is not available for this material, or maybe the temperature is just too high. If you want to compare results from 2 different calculation methods, for instance, or from 2 different designs, we have an option to compare results. If you go to report settings, here we have to set compare, report mode to compare, and in extra settings we have to set use external editor. So this is, I will open the report. This is now calculation according to YF method B, and now I change it to YF method C. I calculate, I open the report, and I have to select here window split. So I have to report side by side, and I have to click here compare results. I will just increase the fonts a little bit so that you see it better. 150. Okay, so we see that it's not a lot of yellow color. Everything is the same here. I would expect the difference to happen here at the tooth root strength. We have one on the left side method C and on the right side method B. I said that the difference here is where we apply the force. In method C, we apply it at the tip. This is our tip diameter, 34,855. And in method B, we apply it lower at the point of single tooth contact, which is in this case 31.2. And then also the stresses are a little bit different, 13 compared to 15.6, and as a result this gives us different safety factors. So this was just to show you how you can use this compare tool to easily see what changed between the designs and how it affects the safety factors or the geometry of the teeth. Okay, we have also so when we do calculation according to VDI 2736 or 2545, we compare the calculated root or flank stresses with the SN curve that we have. In static calculation, we calculate again, this is just to calculate the root stresses. In static calculation, we compare the root stresses with the ultimate and with the yield tensile strength of the material. So if I calculate, it will give us a warning message for the calculation of the static strength. The service life is set to 0 hours because static strength doesn't consider any number of cycles. It basically just calculates one cycle. Go to OK. And here in the results window, then we have safety against plastic deformation. In this case, we compare the root stress with the yield tensile strength, and safety for tensile stress, we compare it with ultimate tensile strength. Let's see the effect of temperature in this case. This is 50. I will increase now the temperature to 100. So the safety factors are for gear 1, 2.7 and 2.9. Let's calculate. So it went from 2.7 to 1.9 and from 2.8 to 2.1. In plastic gears, the higher the temperatures, the lower the safety factors usually. It means that when we are doing a gear design, it's always important to check the safety factors at the most critical conditions, which is usually at higher temperatures and also at high loads. The last calculation that I will show you now is just briefly is we can also calculate according to ISO. If we set it to ISO, we will get a warning message or an error message that it shouldn't be dry running. Okay, we go to oil lubrication and we will get a warning message. Obviously the DIN 3990 and the ISO 6336 are not meant for plastic materials. But in module specific settings, under plastics, we have this setting here, allow simplified calculation according to DIN or ISO. If I press OK, then I have to put here grease first. I also have to increase number of hours a little bit. So we calculate root and flank safety factor, but this is a really rough calculation method, so I wouldn't suggest using it. I would only suggest using it in cases where you want to compare cross-helical gears with cylindrical gears, with, I don't know, phase gear or with worm gear. Only in this case, I would suggest that. Otherwise, use VDI 2545 or VDI 2736. More information about this simplified calculation according to ISO you can also find in the handouts that you can find in the webinar tool. One good benefit of plastic gears is that we are not limited by the traditional manufacturing processes. It means that we can change the tooth, for instance, in the root area, to increase the strength without changing the price of the part at the end, because usually we are manufacturing it with injection molding. We have some options here to improve the strength of the material to the strength of the gears. I will just open the example again from the beginning so that it's not broken. Okay, the calculation method we have now is VDI 2736, and in the tab tooth form, I will add on second gear elliptical root modification. There are 3 inputs to be added for elliptical root modification. This is we can size the start diameter, which is roughly the root form diameter of the gear. We can set coefficient for the curvature. For this, we don't have a sizing button. This is just some experience and trial and errors. And we can also set the arc length at the root diameter. I will show you how this looks like. Tooth form gear 2. I will just show one tooth. Okay, so I will just change the color a little bit so it's more obvious to you. Okay, so the red one is our original tooth form, and the black one is the tooth form that on which we applied elliptical root modification. So with elliptical root modification, we would expect higher safety factors. Let's check if this is the case. This I will move away. So this, we're focusing on gear 2. The safety factor for gear 2 is 4.09 with elliptical root modification. Now I remove elliptical root modification, deactivate, we calculate again, and the safety factor is the same. So this is not a mistake. I did this on purpose. The reason is the following. The root stress in the root area is calculated where the 30-degree tangent touches the root curve. Let's say this is this point. And in this point, we calculate the tooth thickness and we calculate the rounding of the tooth surface at this point. This is all based on the tool geometry. But when we are adding elliptical root modification, we don't have the tool geometry available. So what we do is we have to calculate YS and YF for the whole root area, and then we take into consideration the maximum factor. Let's show it here. So according to VDI or according to ISO or DIN, we calculate the root stress only at one point where the 30-degree tangent touches the root area. But with the graphical method, which I will show you how to activate, is we check the whole tooth, and at the point of maximum YF and YS factor, we calculate the root stress there and we show it in the, then we calculate with this stress as the safety factor. This is according to Obziger. So whenever you are changing something in the root area that doesn't involve changes done directly to the tool, you have to activate the graphical method, otherwise the results will not change. This can be done in tab rating under details, form factors YF and YS using graphical method. I click OK. Now we check again the safety factor. So without, this will also change a little bit. 4078, and now I activate elliptical root modification again. It changed a little bit, so we have a small increase. That's why I said you have to play a little bit with this curvature factor here. And with this you can then increase the root safety factors. You can also get, when using graphical method, some warning messages that it may be or probably producing wrong results. These results have to be checked. This can be checked with contact analysis. If I run the contact analysis now, I will, to make it faster, I will make the uniform face width. So this then speeds up the calculation significantly, and then I can check in the contact analysis graphics, bending stress in root area, gear 2. In this case, you see that the calculation method, the graphical calculation method, doesn't work in this case because we have a sharp decline in the root stresses. So in this case, we would have to play a little bit with the star diameter. Let's try 9.5. And maybe it's just too big. It's not 9.5 but 94, let's say. Let's try again. You see, it's getting a little bit better. This is probably okay because at this point we are far from the highest stress in the root area. In addition to that, we also have the possibility to calculate the root stresses using FEM tool, which is inbuilt, but we don't go into details here. About elliptical root modification and about modifications of the root area in general, we have tutorial 13 available, which you can download from our webpage. What we still have left for cylindrical gears is wear calculation and operating backlash. If we have wear factors available for materials, we can add them manually here in this plus button for the material. 0.5, we have wear factor on both gears, and we will now do the calculation with contact analysis. And under graphics, contact analysis, wear along the tooth flank, let's try gear 2. We have the worn out tooth form, which is the red one, after lifetime. So in this case, after 1000 hours. You see that at pitch point, which is this, the wear is 0. This is because there is no sliding at the pitch point. It's only pure rolling. So in theory, the wear at that point is 0. And this is not completely realistic because we are doing this calculation only in one step. But we have here also an option to do an iterative wear calculation. We set a step of 10. It means that we will do this wear calculation in several steps, so the tooth form will be changing throughout the time to reach the end tooth form. Let's start with 10. We do the calculation. It means that this will now take much longer to calculate because we are doing several contact analysis one after each other. It's going pretty fast because I have equal face width. If I would have different face widths, this would take much longer to calculate. Just a moment. In this case, you see that even at the pitch point here, there is where is not 0 at this point. And also we have the distribution of the wear is much more plausible than what we had before. Okay, if we have wear factors, we also have in the results window safety against wear. We are comparing the worn out tooth form with the allowable worn out surface. This we can set here in the module specific settings. Under calculations, I think we have here permissible maximum wear of tooth thickness. So we allow to, by default it's set to 20%. So if 20% of the tooth form is worn out, this will give us safety factor of 1. And also in the reports we have a separate section for the wear calculation and for the wear safety factors. Last thing on cylindrical gears is operating backlash. This is very important for plastic gears. The problem is, or why we need to calculate it, is because the plastics, when the temperature is changing, is the expanding or shrinking quite significantly because of high coefficients of thermal expansion. In this step, we can set temperature ranges for the housing, for the gears. We can set the permissible temperature difference, and we can also consider the water absorption or the swelling of the gears. And we can also consider excess deviations, manufacturing errors, or runout, for instance. And in this case, when we calculate, this will give us the result for the worst case conditions. if you have enough backlash or not. So the lowest operating backlash in this case is negative. It means that at worst case conditions we won't have enough backlash for the gears to operate. So this will probably happen at the highest temperatures. So the gears will be at the highest diameters and at the smallest possible center distance with the biggest runout. In this case, the backlash, we won't have enough backlash. At the end of the results window, we have a proposition for the smallest possible tooth thickness allowances with which the backlash will be significant enough. So in order to remove the backlash, we would have to enter these values in the tolerance step. We would go here to on input and add here minus 0.16, minus 0.20, 21 for instance, and the second gear minus 0.16 again, minus 0.16 and minus 0.22. Okay, let's calculate again. So in this case, we have now the smallest possible circumferential backlash is positive, so we shouldn't have any problems here with the backlash. We are considering here the worst case scenario, so we're not considering any statistics for the distribution of the tip diameters or for the distribution of the center distance or for the distribution of the runout, for instance. So this is worst case. For modules smaller than 1, there is also in the report a paragraph about the statistical evaluation of the circumferential backlash. Okay, this is what we had to cover on cylindrical gears. Now we are moving on to crossed helical gears. First 2 slides of theory, and then we go to the software itself. Here we have a difference on contact pattern between classical worm gears and crossed helical worm gears. On the top you see the worm gears, where we have a cylindrical worm gear, and then we have a globoidal, the yellow is globoidal worm wheel, and the contact line in this configuration is line. For the crossed helical gears, we have the same cylindrical worm gear, and the yellow one is cylindrical worm wheel, which is basically a helical cylindrical gear. And in this case, contact is only points or ellipses. It means that if we have a bronze-steel combination, the load carrying capacity is 4:1 in favor of traditional worm configuration. But in plastic, maybe the difference is only 20%. So in plastic, we're often using this crossed helical gear worm design because in this configuration we can actually injection mold the cylindrical worm wheel, whereas the globoidal worm wheel cannot be injection molded easily. Why is the difference so small in steel plastic combination? Actually, what happens is that when this starts to operate, because of deflection of the teeth, the load spreads over multiple teeth. So actually the flank pressure is reduced, and also because of wear happening on the contact flanks and running in, basically these contact points soon become the contact ellipses. They become much bigger, and with this they are reducing the flank pressure. About the calculation methods, we have in new VDI 2736 part 3, this is a new calculation for crossed helical gears. There are some limitations for the calculation. We can only calculate metal worm and plastic worm wheel, and shaft angle must be 90 degrees, and module must be bigger than 0.3. What we can calculate is root, shear safety factor, and flank fatigue safety factor, and also we can calculate efficiency. The original VDI 2545 has no calculation method for crossed helical gears, but KISSsoft adapted the calculation so it can be used also for crossed helical gears. So we took classical calculation for cylindrical gears, and we adapted it for cross-helical gears. And we allow also the calculation of plastic-plastic combinations. In this case, we calculate root fatigue data and flank fatigue data. The VDI 2736 doesn't have any flank fatigue data available in the standard, but it says we can use the ones from the cylindrical gear calculations. The problem in this calculation is also in the VDI is that it can happen that the calculated safety factors at the end are just too low because they're not considering this elongated or this extended ellipse contact under load or wear conditions. Okay, let's go to the software. I will open an example that I have prepared. 1.7. For the crossed helical gears, we don't have any temperature calculation available. So you have to enter the temperatures. So this is user input. In the tab rating, we have 3 calculation methods available. The old one from Höchst. This is just steel versus Hostaform. Then we have the modified VDI 2545 and the existing one VDI 2736, which is basically the only valid one. Also here we can do the static calculation. Let's do plastics according to VDI. I have said the limitation is I have to have steel or I have to have non-plastic to plastic combination. So in this case I will put this to steel and steel versus POM. And according to VDI 2736 I do the calculation. And in the results window I have the shearing safety factors. So this is not classical root fatigue, but this is shear fatigue calculation. So we are calculating the shear stress on the gear and comparing it to the allowable shear stresses SN curve, let's say. We also show the contact stresses, but we don't show the contact safety factor because we don't have the allowable flank stresses. In addition to these 2 safety factors, or to 1 safety factor and 1 stress, if the material combination is correct, if we have POM or PA46 or peak, we also calculate wear of the worm wheel, so of the output gear according to Pech. We calculate here safety against deformation, we calculate plastic deformation, we calculate safety against deformation, and we also calculate safety against wear according to Pech for tooth tip or for permitted backlash. More can be found in our help. In addition to that, we also have here the efficiency. The efficiency is governed basically by the coefficient of friction. For the normal calculation, you can set this into details. Mean coefficient of friction. I'll put here a really small value, 0.01, and the total efficiency will now go up from 64 to 90 almost. So the VDI has some suggestions for the coefficient of friction, but it doesn't calculate it based on the geometry. However, if you go to the report in the section where according to Pech is calculated, this is 4A, we have some additional information about the worm design. We are calculating meshing efficiency, we're calculating friction based on geometry, we're calculating efficiency based on friction, we're calculating lubrication temperature, mass temperature, matching temperatures, and all the safety factors that I have already mentioned. When we have let's go to VDI 2545. When we have a steel plastic combination, like we have it in this case, we see that the tooth thickness of both gears is the same. So if we take a look at the root safety factors, we see that on the worm we have a safety factor of 8, and on the worm wheel we have a safety factor of 1.9. It means that our design is really not well balanced, because the steel worm is much too strong compared to the plastic. What we can do is we can try to decrease the tooth thickness of the worm and increase the tooth thickness here on the worm wheel. For this we have to go to module specific settings, and we have to set here maintain tip circle, maintain root circle when changing the profile shift. I will save these two curves now so that we see the difference. And now I will change the profile shift a little bit, minus 0.55, and we calculate. Now we see that the worm is much thinner. We went from here to here, and on the contrary, on the worm wheel we increased the tooth thickness. We came from here to here. This is almost always used when we have a steel or bronze versus plastic in cross-helical gear designs. Let's see. In the graphics, we can also check the contact pattern using the skin model. We have to set this in the module specific settings, generation of 3D. Here we go to skin model. Okay. And then in the graphics, geometry 3D system, we calculate that. And in here we can independently rotate the yellow gear compared to the worm. I will just increase the steps here a little bit. Wrong direction. So always when you're designing cross-helical gears, you should check also how the contact pattern looks like here. With this we can see if we have some problems in the root area of both gears, so that we have some premature contact, and maybe we have to apply some tip relief, or we have to lower the root diameters, for instance. Okay, now we move to the final topic of today, which is Plastics Manager. I will just open the example we have here. Under various, Plastics Manager. The basic goal of Plastics Manager is, with it you can easily add new materials to KISSsoft database, and it can also evaluate root fatigue data if you did some measurements on some test rigs and you wanted to evaluate, or you want to calculate the SN curves. On the first step, we have some general properties, like you select which material it is, if it's untreated or fiber reinforced, exact type of the material. You have density, Poisson ratio, coefficient of thermal expansion, and you have to also add tribological properties, coefficient of friction for oil, grease, and dry running. And you can add wear coefficient, either as one value for the whole temperature range, or you can set also temperature dependent wear factors, like you see it in this table for dry running. In the tab test data, you also have to enter Young's modulus versus temperature. This is necessary for any calculations in KISSsoft, and as an option you can add ultimate strength, and you can also add yield strength, both as a function of temperature. So this is the basic data that you usually get from the material manufacturers. Then if you want to have the SN curves, things get more tricky, because you have to do gear measurements. And if you do gear measurements, you know the geometry of the test gears, which are defined in the KISSsoft file. You know the torques at which the gears failed. You know the speed, you know the number of cycles when they failed, and you have to measure the temperature of the gears. It's not enough to just control the ambient temperature, you have to control the gear temperature. So in case that we have a root failure as a cause of failure, we have to control the root temperature of the gears. So here you see 24 tests. In reality, this would take 3 to 4 months to measure, and it would cost a lot of money. So that's why not a lot of materials have the SN curves available. It's just too expensive and too time consuming. Okay, so we have measurement data here. We can also set how to statistically evaluate it. Usually, according to VDI, we have to shift the SN curves to 10% damage probability in order to be more on the safe side. Let's calculate. In the graphics, we see now the SN curves. This is what we have measured. So blue is at 20, green is at 80, and turquoise is at 100. When we are doing the measurements, usually we are measuring until 1 million cycle, or mostly at not more than 10 million cycle. But the problem is that when we are calculating gear pairs, usually we have, or often it happens that we have more than 10 million cycles. So what we apply here is we have some tools to extrapolate the SN curves. In this case, we have now set permissible stress to 0. Then we can also extrapolate with average slope. Let's do it to 10 million cycles. So we are prolonging the curves, and then we can set to infinity. Or we can do an additional step where we go with smaller slope to, I don't know, 50 million cycles. So we have a nick here, and then again we can go to infinity, for instance. Once we have all the data entered in the Plastics Manager, and if we have also the SN curves available, we can write everything to the .dat file. Let's select a folder. We generate a .dat file, yes, and we can open the .dat file. And everything that we entered in the user interface is now written as a text file, and also the SN curve that you see here as a graph is then written as a text file in the .dat file. By a click of a button, we can also write this material to database, and then this can be used in the normal cylindrical gear, or in the normal cylindrical gear calculation as a new material for our new designs. Okay, this is what we had to cover today. Are there any open questions?
Yes, there was one interesting question in the beginning about fiber reinforced plastic. So we have an option to add into the database that it's fiber reinforced, and especially if you think if we have wear and then you have basically the fibers coming up, of course the material properties change. So the question was, how do these fiber reinforced options influence actually the calculation and wear?
Okay, yeah, that's a good question. Actually, it doesn't affect the wear calculation. The setting for fiber reinforcement is only used in the operating backlash calculation. Let's open the example I had. So if we set the materials, or if we select that it's a fiber reinforced, like one of the lubricants here, fiber reinforced, this is only considered in the operating backlash calculation here. So the reason that we need fiber reinforcement here is in the standard it says that, I will read out, I don't know if you can read it. For plastics, the linear expansion due to water absorption detailed in DIN 3967 is approximately 1/3 of the amount of water absorbed. However, for fiber reinforced plastics, it's only around 1/12 of the volume of water absorbed. So if it's fiber reinforced, we take into consideration that swelling is much smaller than for unreinforced. But for sure, the fibers in plastic will affect your wear behavior. The problem is that we don't know how to consider that in our wear calculation, other than if you expect that the fibers will stick out of the surface, you would then have to manually increase the wear factor. The problem is to which value, I don't know. So it's always important that the fibers do not break out too soon from the surface itself. Either maybe by using long fiber reinforcements or by selecting somehow the appropriate material combination so that the fibers don't do so much damage. It can also happen that they will scratch, for instance, the steel counter gear, but this has to be decided on case to case basis. So we have no more questions for today. Thank you for participating in the web demo. This is all we have time for. If you'll have any further questions, you can send them by email to our info or support emails. And if you're interested in plastic gear calculations, you can also request for a trial version. It's free of charge for 1 month. Then you can order a new one for free. The next plastic gear training in English language is in Bubicon, is scheduled for June 2019. More details are on our webpage, and if someone is interested in the German plastic course 2 days, it's in 1 month. I think it's in 4 weeks time. This web demo is recorded, so the recording together with the handouts will be available from tomorrow afternoon on our webpage. I wish you all a nice day and see you next time. Thank you.